All right, let's get started. So you all have a present for me today. You have homework number 4 that is due today. Exam 1 review is going to be on Monday because we have a celebration on Wednesday. So you know the drill. Be prepared with questions and all that. I saw something. This has nothing to do with anything, but I saw this post on Reddit, and I was like, "This is actually relevant to this class." And it's just kind of cool. This is an image of a bank vault that's being demolished. So it's a bank vault. Look at all that rebar. It's just insane. I think the row value is 1.
How do you demolish something like that?
With time and maybe dynamite, I don't know. They're just chipping away at it. I don't know, but because this boom attachment looks like it has a jackhammer on it, so they're just doing that.
Jet fuel.
I'm using the ambient microphone today. Yeah, that's nothing. I forgot my Surface, so just keep in mind now your voices are going to be on the recording as well. This could go bad. All right. So again, homework 4 is due today. I'll write there. Exam 1 review on Monday, and you all know the drill. When it comes to the exam, one thing you might want to pay attention to, I personally am not going to be here. I'm going to get somebody to proctor the exam for me. But I don't think that really matters. I mean, I don't really need to be here. So today what we're going to do is we're going to continue our discussion on T-beams. I'm hoping to get the analysis portion done today. At least start maybe introducing design procedures. We're not going to finish it in any way, shape, or form, but I figure we can introduce it, and then the idea is that will leave us room to discuss design procedures once we get back from the exam. So with that, let me start a recap, make sure everybody's on the same page. So this is the example we were doing last time, and the big question that we were trying to ask ourselves is this in regards to the analysis of a T-beam. This is where things are really going to get interesting. So when you're analyzing a T-beam, what you have to determine is whether or not the T-beam is a rectangular T-beam or a true T-beam. And what the difference between those two is the shape of the stress block. So if the stress block is rectangular in nature, then it really doesn't act any differently than a rectangular beam. Just because it's T-shaped, it's still a lump of steel at the bottom and a rectangular stress block up top. So the capacity is exactly the same. However, if it's a true T-beam and the stress block is T-shaped in nature, then how you compute VMN is different. So we're going to explore that with the next couple of examples. So we started example 9A last time, and where we stopped was this, and I apologize, I don't have my Surface, I don't have the original notes that we did, but we were looking at this problem, and ultimately, this is where we stopped, right? Because we got B is 60 inches, and then we said, we're done. Okay, so, excuse me. Okay, so what you can do is, if you want, you can say B equals 60 inches, and so this is the actual shape of the beam that we are analyzing, and so the goal is to determine VMN, okay? Now, I'm not going to do this problem any differently, or I'm not going to approach this problem, I should say. I'm not going to approach this problem any differently than any of the other capacity problems that we've had since the class began. So, let me sort of show you what I mean by that. So, whenever you are analyzing a beam, the first thing that you need to do is you need to determine essentially the I'll say determine the characteristics of the stress block. what I mean by that is C equals T, okay? Now I'm gonna formulate this maybe a little bit differently than I have in the past, so here's what I mean by that, okay? Would you agree that if I wanted maybe a little bit more of a general way of stating it, would you agree that 0.85 FC prime times the area of the stress block, so we'll call it A sub block, is equivalent to ASFY? Would you agree with that statement generally? I mean, up until now we've been doing rectangular beams, so we didn't use this term. We just said 0.85 FC prime AB. And then we just said, well, what is A such that C equals T? But would you agree this is a little bit more of a general way of looking at it? Okay with that? So if I wanted to solve for, let's say, the area of the stress block, is ASFY divided by 0.85 FC prime. So that is what? It's 6 square inches, 60 KSI, and then it's 0.85 times, I believe this problem is 4 KSI, all right?
Yes.
All right. And so what does this come out to be? Square inches, right? Do I have a second on that value? We'll make it work. Yeah. All right. Now, here's the next thing I'm going to do is over here off to the side, I'm going to compute the area of the flange. Okay? In other words, I'm going to compute the area of this upper rectangular portion of the beam up here. And so I propose that calculation. It's pretty simple. It's just B times H sub F. And so that's going to be what? 60 inches. So we didn't know what B was at the beginning of the problem. We had to figure that out. So 60 inches times 4 inches. And so that equals what?
240.
There we go. Okay. So let's take a look at these two numbers. Okay? We have the area of the stress block is 105.9 square inches. So what that means is that I need 105.9 square inches of concrete in compression. That's how big my stress block needs to be, such that C equals T. When it comes to my flange is 240 square inches. So let me ask you this. Could I fit the entirety of my stress block in the flange? Yes, I can, right? So what I mean by that is I propose that the stress block is probably going to look something about like this. Here's the beam, and the stress block is going to look something like that. And so I propose then that because the area of the block is less than the area of the flange, this beam is a rectangular T-beam. Now I really want to make sure that makes sense.
Say it again.
Because the area of the stress block is smaller than the area of the flange, we can fit the entirety of the stress block inside the flange, and because the stress block is a big rectangle, then the T-beam is a rectangular T-beam. Yes?
That's opposed to it being a little bit down.
Yes. If this number was, say, 305.9, then my stress block would have to fill the entirety of this flange, and it'd have to go down here a little bit. Does that make sense? That would be a true T-beam. I want to make sure that makes sense. Everybody good? Okay, all right. So when this T-beam, this problem is no different than any of the problems that we've done before. So A is computed the same way. ASFY, 0.85 FC prime B. However, the B is the effective flange width, the entire width of that upper portion of the beam. So this is on the bottom, 0.85, 4 KSI, 60 inches. Up top, 6 square inches, 60 KSI. So what does that come out to be when you compute that out?
1.76.
1.76 inches. Is there a second to that?
Yep.
Now let me ask you this. Does that value make sense? Let me go back a slide. How deep is the flange? 4 inches. So if the stress block is going to be rectangular, shouldn't A be less than that? And that's what we got. A was about 1.76 inches, so that makes sense. It's sort of a check as to what you're doing is correct. So if you got that, then MN is ASFY, D minus A over 2. So that's 6, 60. What's D? Anybody have a value on that? 24. Now, if I calculate this as is, what are the units going to be?
Inch kips.
Inch kips. So I'm going to convert to get foot kips. Excuse me.
690, 3.6.
I have a second on that?
Yeah.
All right. Now the goal of this problem is to determine phi MNs. Tell me what to do next. I'm not telling you, you tell me.
Epsilon's 2.
Okay, and to do that,
0.003 times D minus C or C.
what's the problem?
We need a C.
There we go. We need a C, right? You're exactly right, but you went one step further. We need a C. So how do we compute C? A over, there you go. A over beta 1. So 1.76 inches over beta 1. What's beta 1? It's 0.85 for any concrete that has compression strength less than or equal to 4 KSI. Okay, and so what does that equal?
2.07.
2.07. No second on that? So epsilon sub t is, just as Austin said, 0.003 d minus c over c.
.0318.
Okay. And so what does that mean?
Tension control.
It's tension control. Remember, it's not 0.05, it's 0.005. Okay? This is greater than 0.005. Usually with T-beams, because of their nature, the strains have a tendency to be a lot higher, which is kind of a good thing. So that means that phi is 0.9. And so what is phi MN? What do you think? was an example of a rectangular T-beam. If you can guess what this problem is, I think it would be time for you to go to Speedway and get a lottery ticket. That's a joke. So if last one was a rectangular T-beam, what by chance do you think this one's going to be?
True.
No, it's a rectangle. No, I'm just kidding. Now this one is going to be a true T-beam, and I'm going to show you how. So the parameters are a little different. I mean, and one other thing, I went ahead and gave you the B value because I've already shown you how to compute that once. I'm a big fan of not doing the same thing over and over and over again. You're going to be here, I'm going to make the time valuable. So we're going to do the same thing. We're going to compute VMN. However, the beam is, you're going to find out, is going to be rectangular in nature, so it's going to be a true T-beam and not rectangular in nature. It's the same material characteristics. The D is 30 inches, B sub W is 14. We have a B of 30 inches, and this is, the steel has increased. We now have 8 number 10s. So what I'll do, I'll go ahead and copy this image over. Woo! That's big. That was the sound effect for me as well. Okay, so here's the beam. Let me here's this. I'll give you a sec to sort of copy that now. Oh, one other thing. I'll give everybody a sec. Everybody good? Okay, alright. Now, like I said, spoiler alert, this is going to be a true T-beam, but let's do our diligence and make sure. So let's start off with equilibrium. Or, again, C equals T. So, we say 0.85 FC prime times whatever the area of the stress block is got to equal ASFY. So, the area of the stress block is ASFY divided by 0.85 FC prime. So that's 10.19 square inches, that mass by the way, times 60 KSI over 0.85 times 4 KSI, and that equals what? Say it again.
179.8.
179.8. Do I have a second on that? Okay. Let me write this up here because I'm going to use this space over here in a second. Okay. All right. So I think you can probably see what's going to go on. If I can compare this against the area of the flange, the area of the flange is BHF, and so that is 30 inches times 4 inches, and so that's 120 square inches, right? So what's happening is this, okay? The stress block, see, I don't have enough room in the flange to fit the stress block. The stress block has probably got to look something like this, because it's going to take up the entirety of the flange and then some. Right? And so that's really what the stress block is going to look like. Okay? So would everybody agree that this is going to be a true T-beam. Am I okay with that? All right. Now, how do we handle that? Like, how do we, what do we do? Well, let's be clear on some notation, okay? And I want to make sure everybody's clear on this, okay? This dimension right here, that dimension is still A, okay? We always define A from the tippy top of the beam to the bottom of the stress block. That's what A is, okay? So just because we have a differently shaped stress block, that does not mean A goes from here to here, okay? In fact, this dimension right here, that dimension is A minus HF, okay? I want to make sure everybody's clear on the notation, okay? Now, here's what I challenge you to do. We have area of the stress block. Help me out. What is the area of the stress block? And I want you to tell me what that area is symbolically. Now, I'll help you out. For the sake of what we're doing here, let's split it up like that. So, symbolically, what is the area of the upper portion? B times HF, but haven't we already computed that? That's the area of the flange, right? So, we could say it's the area of the flange plus something. Plus that block down below. Now, how wide is that block? BW. How tall is that block? There we go. So this is B sub W A minus H sub F. Now, if I look at that equation, what don't I know? I don't know A. So I can use this equation and I can solve for A pretty easily. So I can subtract A block minus A flange equals BW minus HF. I can divide. And then what do I do? Add the HF over. So A equals A block minus A flange minus BW plus HF. And so that's going to equal 179.8 square inches minus 120 square inches over 14 inches. Plus H sub F. And so what does that come out to be?
8.27.
8.27. So I'm going to round that to 8.273. I'm just doing that so we see that the numbers that we're using are, I give them a little bit of depth so we know what we're looking at. Is everybody okay with that? Okay, I have a second? Okay. Now, what I am going to go ahead and do so everybody's clear, I could go ahead and compute MN, but before I do, I'm just for the sake of discussion, just to get it out of the way, I'm going to go ahead and determine C and epsilons and T and get my feed value. I'm just going to go ahead and do that now. There's nothing stopping me. And the reason why I want to go ahead and do that now is because there's no difference in this computation between what we did before and what we're doing now. Once you have the A value, it's exactly the same as before. We start off with C that is what?
9.73.
And then we calculate epsilon sub t. Exact same formula as below, or as before. And so that equals what?
0.0065.
Do I have a second on that? Okay, and so that's greater than 0.005, and so therefore B is 0.90. So I wanted to go ahead and just sort of like do that off to the side, just so there's no ambiguity that that is any different. It's exact same computation as before. Okay? Everybody okay? Now that's the phi value, that's easy. But what about Mn? Okay? Mn is not going to be the same. We can't use ASFYD minus A over 2 because that computation assumed that the stress block was a rectangle. It's not. It's a big T shape. Okay? So I want you to bear with me. I'm going to do a little bit of artwork up here on the slide, and I think you'll see where this is coming from. So just bear with me. Give me a little bit, and you'll see what's going on. Everybody got this? Okay. Now, I'm going to show you how we do this, and there's a reason why I'm doing this in this specific way. So the nominal moment capacity Mn. Okay. So what we do here when we compute nominal moment capacity of a true T-beam is this, is we end up taking the nominal moment capacity of what we call the flange couple plus the nominal moment capacity of the web couple. And you're like, well, that's great. What the heck does that mean? So just bear with me. All right. So here's what we've got going on. We've got a T-beam all right. We've got some steel down here. And it doesn't matter how many bars it is. I'm just putting, this just for the sake of discussion. And I have a stress block that looks something like this. Okay? Here's what we're going to do. We're going to take this stress block and we're going to split it up into two different couples. Okay? So here's how we do this. The first thing that we do is we split this up into the flange couple. So the flange couple looks like this. Like I said, just bear with my artwork. Okay? And then this is going to have, let's say, some steel associated with it. I'll do 4. And then what we're going to do is we're going to add that to the following section here. So we're going to have sort of this beam like this. And this is going to have a stress block like this. Maybe this one has, I don't know, 2 of those bars associated with it. I'll explain that here in a little bit. So we're going to have Mn equals Mnf plus Mnw. Okay. That's sort of what we're doing to handle this. Yes.
It's just because it's easier to split up this way, or is this the only way? Like if you
No.
split up the top part and then the tiny bottom part.
That's a great question. And so the answer is this. The reason why we split it up this way is because when here in a second when we start discussing design procedures, you're going to see how it's a little bit more convenient to split it up in this fashion. And you'll see here in a second, okay? Also, here's another thing. When it's all said and done, it might not seem intuitive, but the actual equations themselves are a little easier, that symbolically. That they end up being a little easier to deal with. So, okay, let's also recognize that this has sort of a, a phantom T-shape out there. And so what I'm doing, first off, the reason why I'm splitting it up, at all, is because instead of having to deal with a T-shape where I have to compute the centroid of that T in order to do moments, I'm splitting it up into rectangles where I really don't have to deal with complicated centroid computations, because it's going to be a pretty straightforward assessment. Okay, let me show you how this works. All right, first off, let's put some dimensions. What is this dimension right here? That dimension up top of the flange couple. Let's start doing some dimensions here. What is that dimension? Well, no, I'm talking symbolically.
BW.
That's BW, right? And what is this dimension? That's B. So would you agree that B minus BW would be both of these? Like half that is this, half that is this. So B minus BW is that total length right there. Do you agree with that? Okay. What is this dimension right here?
HF.
That's HF. And what is this dimension there?
D.
That's D. Everybody okay with that? What is this dimension right here?
BW.
BW. What is that dimension?
This HF.
No.
HF.
That's A, right? Because remember, A, yeah, see, that's going to be A. And this dimension right here is still D, right? Okay. Everybody with me on there? All right. The reason why these dimensions are important is because how did we determine moment capacities in the first place? We said we're going to take a force times some moment arm, right? We're going to do the exact same thing here, okay? We'll show you how this is going to work. Let's take a look at the flange couple. What would be an expression of that compressive force here? In other words, the stress block. How would I determine that force? Well, I propose we take 0.85 times FC prime times the area of those blocks. What is the total area of those blocks? How tall are they?
HF.
HF. And how wide are they total?
B minus B minus
B minus BW, right? The total, so B would be this entire width. And if I take that out, that's these two added together. So that total force is going to be 0.85 FC prime B minus BW times HF, right? Let's compute that. 0.85, 85, not 0.5. 0.85 for KSI. Now, what was B? 30.
30.
What was BW?
14.
And what's HF?
4.
So what is that?
272.6.
What about CW? How would we do that?
W times A
What?
times 0.85 times FC prime.
Okay, 0.85 FC prime times what?
BW times A.
Times BW times A. So 0.85 FC prime AB. Only instead of B, it's B sub W. So 0.85 FC prime A BW, right? So this is 0.85 for KSI. What was A again? And BW is 14 inches. And so what does that come up to? 393.8. Do I have a second on that?
Yep.
All right. So what, just over here off to the side, what would the total compressive force be? It'd be C sub F plus C sub W. Say it again. 611.4 kips. Everybody agree with that? What is the total tensile force? How do you determine that? No. How do you determine it? Okay, and follow that thought. No.
ASFY.
There you go, ASFY, right? Let's compute them independently. What was AS for this problem?
10.19.
And so what does that come out to be?
611.4.
We call that reason for a marker drop. What's that? I know, it wasn't it? That's a check when you're doing a T-beam analysis. You're computing your compressive forces separately, and you compute your tensile force, and the MC has to equal T. So it's a check to see whether or not your math makes sense. Is everybody okay with that? Okay, now I don't remember who asked, but somebody asked, why did we formulate it in this way? The reason why we formulated it this way is from a design standpoint. See, if you look at the flange couple and you look at the web couple, the flange couple does not have A in it at all. There's no A term here. And for the web couple, there is an A, but there's no parentheses. So that's why we formulated it this way, because it's easier from a design standpoint. Everybody okay with that? Now, this only gets us half the way there. Those are the forces, but we need the moment arms, okay? So let's see if we can derive a moment arm for the flange couple and for the web couple. So how far is it symbolically from the center of this steel to the center of that compressive force for the flange couple? There you go, D minus half of HF. So this is going to be D minus HF over 2. What about C sub W? How far is it from the center of the steel to the center of that compressive force?
D minus A over 2.
D minus A over 2. Is everybody okay with that? So this is D minus A over 2. So if you want to know how do we compute MN, we take C sub F times D, whoa, got away from me, D minus HF over 2 plus C sub W times D minus A over 2. So this is what I meant when I said this right here is MNF and this right here is MNW. Everybody okay with that? So we're splitting it up into two different couples, okay? And so that's going to be 217.6 kips times 30 inches minus 4 inches over 2 plus 393.8 kips times 30 inches minus, what was A again? 8.273 inches over 2. And so chug that out, what does that come out to be? I got it.
$16,277.8 inch kips.
Right? Have a second on that? And so how many foot kips is that?
1356.5.
Okay. Now that's MN, what am I missing? Phi MN, and what was phi? We did that earlier. So phi MN is what?
1220.8.
So at top there, where you put the 4 bars in the one and the 2 bars in the other, does that actually matter?
That's a great question, and the short answer is yes. See, and let me sort of explain that, and that'll become a lot clearer when we get into design mode. So you would agree that C equals T has to be the same no matter what, right? Well, this is a different compressive force than this one, right? Do you agree with that? So if this is 217.6 kips, I would argue that there's a certain amount of steel that corresponds to this, and there's a certain amount of steel that corresponds to this, right? So this is going to have a little bit of steel, this is going to have a little bit of steel. Now theoretically, when I add them up, it would equal this, right? Okay with that? When we get into design mode, if we're designing a true T-beam, that's exactly how we handle it. We figure out how much steel we need for this, how much steel we need for this, we add them up, and that's the pattern that we pick. But you're exactly right. That is, does it matter? Yes, it does, especially in design mode. Is everybody okay with this? Let's talk a little bit about design. We're not going to get into actually doing any problems, but I do want to highlight this process because it's really important. Okay? Now, one thing to keep in mind in T-beam land is almost always a known cross-section design. Because even if you didn't know what the beam looks like, you could design the beam independently and the slab independently and lump them together and then start doing a T-beam design. So even if you're designing from scratch, usually in T-beam design, you know what the beam looks like. So you don't have to assume a beam self-weight or anything like that. All you have to do is just determine the amount of reinforcement. So here's sort of what we got to do, okay? In our 2 previous examples, we noticed how we have a rectangular T-beam and we have a true T-beam, and that case depends on the depth of A. You know, if A is below the flange, then it's a T-beam, but if it's above the flange, it's a rectangular T-beam. So here's our design process, and I want to sort of show you how this works. Now we're going to use this rho value, okay? Because it's scientific, we know what the beam looks like, so we can solve for rho. However, this rho value sort of assumes that it's a rectangular T-beam, so let me walk you through the process. All right? Here's rho. We can take that rho and we can back calculate what A is pretty easily. I think it's a lot clearer if I step by step it here. Okay, hold on. I'm getting too ahead of myself. Let me go here. So don't worry, we're gonna go through this very in a very detailed fashion next time because I don't have time to go through it all right now, but I want to just sort of highlight how this is going to work. So this is how T-beam design is going to work. We're going to compute the factored moments on the beam just like we had before. We don't need to assume the beam self-weight because we got that. We assume a phi value is 0.9. We're going to have to check that later. And we're going to, watch this. We're going to assume that the neutral axis is in the flange. So we're going to, at the very beginning of a T-beam problem, we're always going to assume that the T-beam is rectangular. Okay? We're going to calculate the rho value, and then what we're going to do is we're going to take that rho value and we're going to sort of back calculate A. So the idea is we're going to calculate how much reinforcement we would need if the beam was rectangular, and then use that reinforcement ratio to say, well, if we actually use that much reinforcement, would we have a rectangular beam or would we have a true T-beam? And so if the beam is actually rectangular, the way I've set up these procedures, we'll go to step 5. But if that's wrong, if that assumption was incorrect, then we skip ahead a few steps to step 8. And so what I have is here's my steps for if it's a rectangular beam, and then here's my steps for if it's a true T-beam. And don't worry, I'm gonna go through this derivation in some pretty significant detail next time. We don't really have time to discuss it today, and so I definitely think that it deserves some merit. Actually, I would say next time. I'm not going to discuss this till next Friday, so I'm definitely going to need to sort of slow this part down. But like I said, we've got time. So with that, you all have turned in homework number 4. Work on getting that graded. Monday, come prepared to ask questions. Wednesday, we start celebrating. Sound good?